Hello, my name is Zhao Chen. I'm the product manager of Flex 3D. Here is my honor to introduce Professor Katerina Ziotopoulou. Okay, okay. And Katerina is an associate professor in civil and environmental engineering at the University of California, Davis. She received her 5-year diploma in civil engineering from the National Technical University of Athens, Greece, and her master and PhD degrees from University of California at Davis. She specialized in soil dynamics and geotechnical earthquake engineering, with an emphasis on investigation of ground failure due to earthquake-induced liquefaction and cyclic softening. She combines the development of advanced numerical tools with multi-scale experimental methods and data analytics, the establishment of validation protocols, and the upscaling the system-level analysis of case histories. She is passionate about ensuring tech transfer to the industry through many professional courses. She has been honored with, for example, ASCE Casagrande Professional Development Award, National Science Foundation Career Award, and the International Association of Soil Mechanics and Geotechnical Engineering Young Researcher Award. And let's welcome Katerina for this keynote.
And Zhao is also from UC Davis, which makes this particularly meaningful for me. So good afternoon, everyone. Thank you very much for being here today. And I would like to particularly thank ITASCA for making all these amazing software and inviting me to be here today. So before I do anything, I want to acknowledge my co-developer and collaborator in the journey. I will share with you Professor Ross Boulanger from UC Davis as well. So my typical problem is that I'm surrounded by geotechs, but not numerical modelers, and this is not the case in this room, which is great. As Al mentioned, my focus is to enable the performance-based assessment of liquefaction or cyclic softening effects on civil infrastructure. And admittedly, the estimation of these hazards, especially when we have the ground coming into play, is particularly challenging. So we're doing everything we can to understand it, quantify it, and then incorporate it into our decision-making procedures. In this, nonlinear dynamic analysis come into play, and they are proven to be great tools. And what we do, the element level is represented by the constitutive model and how that is activated by the different loading paths that may dominate in each system. And then we have the system level, which becomes a little broader. It's the assembly of the tools that we have, the platform, the model, or the numerical choices we make, the soil properties, and then the selection of ground motions. And it becomes a larger thing to undertake. Now, we will all agree that the quality of such an analysis depends on many technical or non-technical factors, ranging from the protocols that we use to calibrate our tools and fine-tune them, the quality of site characterization work, the input ground motions. Those are typically proven to be a great source of uncertainty. And then we go into other issues like the allocated time and budget and the expertise of the analyst. In any case. So for today, I will focus only on constitutive modeling aspects, particularly for this audience. And I'm going to spare you the details and nasty equations, but I'm going to share with you 3 lessons we have learned over the years that hopefully will be transferable to the different disciplines with which everyone is coming in here today. So I will first start of how we went about developing plasticity models for earthquake engineering applications. Somebody asked me today, since when have you been working with FLAC? Since 2007, FLAC 5 was the one back in the day. But in 2010, we started developing PM for sand. That is a plasticity model for sands and earthquake engineering applications. And then we also work with PM for silt, which is a silt plasticity model for earthquake engineering applications. And then in 2012, we transitioned to implementing it in a DLL, and then we entered a more stable phase in our lives in version 3, and now most lately with FLAC 8 and FLAC 9. And in parallel, in 2018, we started with PM4SIL, which now exists in version 2.1. All the gory details, papers, equations, you can find them in our website, and I can share anything you want after this talk. Now, the continuous validation has been a key throughout this process, and we would have to acknowledge that now these models have been implemented in other platforms, which allows us to vet them against each other, have more tools to capture uncertainty, provide more options for people to do their work out there. But I will point out is that we have not been involved in the implementation in these platforms, so I cannot speak to them. Now, in terms of the framework, we followed the framework of the Dafras-Manzari model, and this comes with very particular importance because it's a great framework, and it comes with 3 principles. It's critical state based, meaning that whether in the SAN or the SILT framework, we follow the critical state line and the critical state framework, basically very eloquently combining the effects of confinement and packing and their effects on the behavior of the model. They're both stress ratio controlled, meaning that you need to change the stress ratio in order to induce plasticity, and then they follow the framework of bounding surface plasticity, essentially in this space tracking a very thin elastic range, and then 3 surfaces, which basically by measuring the distance of your stress condition from them, you can calculate valuable quantifiers like dilatancy, plastic modulus, and dilatancy, plastic modulus. These are the 2 ones. 2 of the principles in developing them have been utility and usability, and those are addressed by very specific choices. The utility has to do with having a model that can work across the broad range of conditions that you find in real case scenarios in practice. So we worked at the equation level. These are not just dials that you calibrate and you change. The functional forms of the equations drive the responses. And building from the Dafras-Manzari framework, we cast the models around the relative state parameter. We added beyond the fabric tensor. We can talk about these details later. We added fabric history and a cumulative fabric term, which means that we can track damage. And then all the key parameters in the models are anchored around that. And then we also constrained dilatancy based on Bolton's relationship, which provides to be really useful for being interested in peak friction angles and residual or critical state friction angles. That has to do a little bit with utility. Usability has to do with having input parameters that can be easily obtained or reasonably easily obtained in practice. So we have 3 primary parameters. 1 for strengths, basically, relative density in PM4SAN. In PM4SILT, that would be the undrained strength, or in a ratio format. The shear modulus coefficient, you need something for your low strain behavior to capture the stiffness, and then a contraction rate parameter that you calibrate against strengths. And then going back to utility, there's also secondary parameters that can be either left to their default values, meaning that all these equation level calibrations will be activated, but should you have more site-specific or lab-specific data, those can be activated with care and with care. So why did we do all of that? I talked about a broad range of behaviors. And if you're familiar with the cofaction evaluations, then you don't have to be. These are just some schematic illustrations of behaviors that are typically guiding what we do, from cyclic strengths to the effects of loading duration, overburden effects, sloping ground effects, cyclic mobility, modulus reduction and damping curves, and then residual strengths. And we have to recognize that we have to try and be simple, but sometimes for complex problems, we need complex models that can also provide flexibility. The other thing we did was document everything, and we have our manuals publicly available, and wherein we document what the model can and cannot do for a broad range of loading and soil conditions. And some of the limitations currently are that it's implemented in plane strain problems. We're working on a 3D version, should be out quite soon. The formulation does not have a cap, meaning that if you are on a constant stress ratio path, there's not going to be any plasticity, and we have omitted the load angle dependency. And it's important important for people to know that, such that they don't try and use the models for things that were never within the scope of that development. And we find that it's important to advertise these things so that people can be guided. I will switch now to some considerations for validation and calibration. So I'm going to open up a little bit, recognizing that there's many more other things that come into play when you use constitutive models for such exercises. So I'm going into the context of nonlinear dynamic analysis, and in these interactive bubbles, we basically want to look in our analysis model right there in the middle, and the evaluation of the seismic performance of any geosystem or soil structure system, whether that's deterministic or probabilistic, that involves synthesizing information from site characterization, past performance observations, loading conditions, and having a good grasp with those, and then doing the dynamic response analysis, and then propagating these into a damage assessment and the consequence assessment. And now you're going to have uncertainties in any part of this bubble, and those are going to be propagating downstream as we go towards our decision-making process. So as we do these evaluations, it's important to understand the broader context and know when to allocate effort. And this is one of the questions we get, people trying to fine-tune a teeny tiny parameter that ultimately in the broader scheme of things does not matter. And it's important to recognize that, and it's important to take the step back before you embark on any exercise and suffer perhaps in the process. The other question we get typically is how to calibrate the model, and we have separated, and I think this applies quite broadly. There's the traditional mechanics of materials calibration approach, and there's more of a generalized approach to calibration. What you would do in the more traditional one was that you would use lab testing to determine one by one the parameters of a model and directly simulate a lab test. And this implicitly assumes that the model can extrapolate to other conditions, but that needs to be checked. And an approach like this would work great for simulating a lab test, but potentially would not apply to some of these more broad conditions that I'm showing here in practice. When you go into the generalized approach to calibration, which is what we have been trying to promote from the use of this model, not so much in their development, goes to the fact that you're synthesizing first all of the information you have at your site, from your lab test, the geological information, past observations, and so on and so forth. You set target responses after having reconciled any differences, and then you calibrate a model that will honor those responses. The models, the constitutive models, doesn't have to be PM4, it could be any model, will not reconcile issues that you have from the field characterization, and it's important to separate that. So you have two choices. On the left, that's a traditional one. You're characterizing the soils, and on the right, you have calibrating the models. And this separation, it has the benefit of clearly separating the problems that can arise due to data inconsistencies from the problems that arise from model calibration. And we find that this is a message that we need to be reinforcing. So on the left, you would be estimating key properties using the best means available to you. You're recognizing the limitations in each data source, and then you embark on the calibration. And that's where you select input parameters, and then you have a calibration that depends on the behaviors and the data you prioritized in the process. An example for this has to do with the very simple notion of undrained shear strength. So here I'm showing plots of deviator stress versus mean effective stress, so basically an undrained path, starting from an initial void ratio, shedding effective stress, building excess pore pressure because it's undrained, and then eventually landing on the critical state line. Its counterpart in the critical state domain is horizontal because you're not changing volume, so your void ratio stays constant, and you start, in this case, from elusive critical, and then you move to the left. Now, it's important to realize, first of all, yes, the initial state is captured by an initial void ratio. The undrained strength is realized at the critical state. My life, even when I was a student, improved significantly when I just realized that constitutive models are nothing but the translation of physics into geometry. And all the lines that we have are just vehicles that enable some behavior. In this case, the critical state line is the vehicle that enables this undrained strength. Okay, so when it comes to calibration and building on what I just said earlier, you have one approach: set the void ratio and the critical state line. In this process, though, you're also dictating the undrained strength. And this is something that many people do, waiting for the model to tell them what the undrained strength is. But I would make a pitch for us to consider approach number 2, where you set the void ratio and you set the critical state line at a location that will eventually give you the undrained strength that you want, such that you force your model to give you something that you have decided from that characterization. And we find that this is usually more tractable and more responsible in practice. So that's one. Now, I talked about selecting the models and advertising what they do and what they cannot do. That is one, but then the evaluation of whether a model is for you or not has to do with understanding what type of system you're dealing with. And if the model is not capable of doing sloping ground conditions, for example, it does not matter if you're doing a site response analysis, and so on and so forth. So we need to always anticipate what constitutive behaviors are important to our system's response, and that doesn't take long to do. Now we go back to our shopping list that I showed before, and then we have to decide what properties should be prioritized in calibrating the model for a system. And then that choice must be confirmed by running at least some initial stage analysis and checking that the things we believe the model can do are actually able to be done. And the way to visualize this is by going into this loop of probing the model, going into the element, going to the system, and then spending some time to make sure that we conquer all parts of this process. And here I'm showing a dam. It doesn't have to be a dam, but it's important to realize that when you're validating a numerical model, you're validating the set of all these choices, and in the process you have to have validated all the individual components that go into the analysis. So when we say that Katerina has validated an embankment dam with PM for sand and PM for silt, that only talks about this combination of capabilities and systems. Perhaps Katerina is not able to do a retaining wall, or perhaps the platform and the constitutive model cannot handle a system. So we need to be exercising and interrogating our models for other systems as well, both in the parts and in the system. And of course, with platforms like the ones we're all working with here, the issue of verification and validation of the individual components becomes very, very tractable. So that was the second part. And now for the third part, I want to wrap up with some considerations for modeling other materials and conditions. And this is to answer the question, can I use PM for sand or PM for silt for that soil? I have a rock fill. Can I use it? What should I do? And the question is, I don't know, how much have you characterized your material and what do you think the model can or cannot do? So the answer is yes, provided that you recognize that both models are just calculators. I talked before about the different surfaces being vehicles, and that is really just having to do with understanding what the principal components that are available to you are. When we go to other challenging geomaterials, yes, they're more challenging and difficult to characterize. Sometimes they're poorly understood, but we have emerging challenges in our field, and we always have something new to deal with. So that is definitely something to recognize. But ultimately, we still need to make decisions, and we still need to represent them in our models. So we can focus on approximating stress strain behaviors and having a good grasp on them. And ultimately, it has to do with to the extent to which the constitutive relationships can match what you believe your soil is doing after having spent some time in the site characterization. And then, of course, that assumes that one is properly trained on having a good grasp on the model and the constitutive components. So my concluding remarks back into basically every one of my sections today. Development of constitutive models need to address utility and usability. We did that with the input parameters and the generalized calibration against what we know from the field. It's always a good idea to separate soil characterization from soil calibration. understanding the validation space, the loading paths that you expect, how your model will respond to those, what is going to get activated, and go into that loop of checking the element, going to the system and back. And then being able to successfully use such constitutive models. Again, this is a very broad lesson. It doesn't apply to our models necessarily. They're just calculators, really advanced calculators. And if you know them very well, you can fine tune them to do whatever you want for you. Within reason, you have to understand them. So with that, oh wow, I'm on time. Questions are welcome, and thank you very much.
And that so we can design for like ultimate like peak strength ratio and also the residual strength ratio. So and if we use different parameters, we may get different like mechanisms in terms of the failure mechanism. So which one? I personally, when I looked at the manual from the Constitutive, it was not clear to me. So is it going to be like a residual shear strength ratio, or is it going to be a peak shear strength ratio? I understand that it's something related to critical state line, understand the loading, but also my understanding is that it's going to be like peak shear strength ratio, because if we apply just the residual shear strength ratio with the whole material, which we don't know where it's going to liquefy. So that's actually my
so the input parameter is the undrained shear strength at critical state for earthquake loading rates. Okay, so that's one, right? So it will be a little bit bumped up compared to monotonic conditions. Okay, now how the critical state relates to your peak one has to do with your sensitivity. Okay, the sensitivity is basically what is the post-peak strain softening that you get. You can control that by one of the secondary parameters, right? And by controlling one of those secondary parameters, you basically back connect your undrained, sorry, for you, it's going to be on the right, your undrained strength at critical state with your peak one. Okay, and you can do different variations. You can have sensitivity of 5 or sensitivity of 1, where basically your peak is your critical state, right? And that is up to you, right? If you have vane shear tests, if you have any lab tests, we usually have some sort of information on that. And if that is your critical, not in the problem, probably this is something to parametrically vary and see if it alters your answer at the system level. Yes, but the residual is a direct assignment and the peak one is not.
Yes.
It's an indirect assignment. Yes.
Thank you.
We still have time to.
Oh.
How painful is it to go to 3D, and how important is it to go to 3D?
It was not very painful because we had a great student to help us, and we had built a lot of experience with everything. It is necessary, from what we hear in industry, for dam projects and foundations, lots of research on footing and different types of footings and those types of interactions. So we kind of need that there. We know people are moving in that direction. The flat platform is becoming faster and more attractable to use. So it clearly it hasn't been the top priority over the last 10 years, but I think it's time. Yeah. And also, I mean, for me personally, when we were between FLAC 8 and FLAC 3D7, when I touched FLAC 3D7, I was begging for the day that FLAC 9 would come out. And now my life personally is significantly improved. Yeah.
When you are calibrating, you are using uniform loading cycles in the shafts, for example. Have you tested to see that if we have a irregular loading during the just cycles in the shear test, this % or CT can capture the behavior?
Yeah, that's a great question. The question was whether we have tested with non-uniform cyclic loading as opposed to the typical one that we do in the DSS test. Yes, we have done a lot of tests in the DSS device with different air pluviated specimens, and we did different protocols of starting with a larger amplitude and then reducing and then increasing it back up just to see how cyclic mobility will change. And that was a lot of the driver behind going from version 2 to 3. It performs well. you can fine tune it to work better. The equations can capture these progressive reductions and increases. If you dial the numbers and if you have lab specific or site specific tests, then it's going to capture them as well. Yes, we have done it.
Have you published this result?
Yes, Canadian Journal.
Thank you.
Yeah, I can share it with you.
Thank
Yeah.
you.
Any other question? I have a question. So this model similarly is for plane strain condition. Yeah, it's applicable to anisymmetric condition.
The plane, you mean the plane, if I run PM4 as a plane strain condition?
Yeah, anisymmetric condition like a rotation.
Oh, we need the 3D for that.
Oh,
We cannot do axisymmetric with that. That's why in the manual we show some plane strain compression test as a cheap proxy for triaxial. But until we have the 3D, it's not going to do the real axisymmetric.
I have one more detailed question. How do you assume the out-plane stress?
As the average of the other two.
What's the average?
Yeah.
Oh, okay. Sigma 1, sigma 2.
Yeah.
That plane.
Yeah.
Okay. Any other? Yes, thank you very much.
Thank you.